Welcome to this session on problem decomposition and computational thinking. In the next 5 minutes, we will focus on how to break down complex problems into smaller, manageable parts. We'll use two case studies, an automatic coffee machine and a greatest common divisor, or GCD, problem from mathematics. Our goals are simple. First, understand clearly what we mean by problem decomposition. Second, practice decomposition on a real-world system, the coffee machine. Third, practice on a numerical problem, the GCD. Finally, see that the same way of thinking works in very different contexts. Problem decomposition means taking a big, complex task and breaking it into smaller, simpler subtasks. We do this because smaller problems are easier to understand, easier to design, and easier to implement. In engineering and computing, decomposition is essential. Large systems are always built from smaller modules that can be developed and tested separately. Let's start with the coffee machine. Before decomposing, we must understand the problem. We ask, what coffee can the machine make? In our case, 4 hot drinks: espresso, americano, cafe latte, and macchiato. What does the machine need from the user? A drink choice and a payment method, either cash or QRIS. Comp think BRP Rev Submit. What does the user receive? A cup of coffee and status messages, for example, payment successful or stock empty. And finally, what resources are required inside the machine? Coffee, hot water, milk, and access to a payment system. Now we decompose the coffee machine into modules. First, an ordering module that displays the menu and records the user's choice. Second, a stock checking module that verifies whether there is enough coffee, water, and milk for the selected drink. Third, a payment module. Inside this, we can decompose further into cash payment and QRIS payment. Cash payment counts inserted money and checks if it is enough. QRIS payment shows a QR code and waits for confirmation from the bank server. Fourth, a coffee-making module that prepares espresso, americano, cafe latte, or macchiato according to a recipe. Finally, an output and status module that delivers the coffee and displays messages to the user. Each module is simpler than the entire machine and could be designed and tested separately. Now we move to case 2, a mathematical problem, the greatest common divisor, or GCD. First, let's understand the principle of GCD before we think about decomposition. Suppose we have two positive integers which we call a and b. The greatest common divisor of a and b is the largest number that divides both of them exactly with no remainder. Let's look at a simple example with 12 and 36. The divisors of 12 are 1, 2, 3, 4, 6, and 12. The divisors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, and 36. If we compare these two lists, the common divisors are 1, 2, 3, 4, 6, and 12. Among these, the largest is 12, so we say that GCD of 12 and 36 is 12. In other words, the idea of GCD is based on two simple actions: finding all divisors of each number and identifying the largest divisor that they share in common. On the next slide, we will use this idea to decompose the GCD problem into a few clear subtasks, just like we did for the coffee machine case. Now let's look at how we can decompose the GCD problem in a very general way. Our goal is to find the greatest common divisor of two numbers. The inputs are simply two positive integers, which we'll call a and b. The output is one number, the largest number that divides both of them exactly. Instead of jumping directly to a clever formula or specific algorithm, we first think about subproblems that a human could do by hand. First, we find all the divisors of a. These are numbers that divide ai with no remainder. Second, we find all the divisors of b. Third, we compare the two lists. We look for numbers that appear in both lists, those are the common divisors, and then we choose the largest of them. That number is our greatest common divisor. This breakdown is already a form of problem decomposition. Later in the course, we can turn each of these subproblems into more detailed steps, and then into flowcharts or pseudocode. For now, what matters is seeing how a single big task, find the GCD, can be expressed as several smaller, clearer tasks. The key takeaways are: always clarify the problem first. Identify the inputs, outputs, and resources. Then, deliberately break the big task into smaller, meaningful subproblems. That is the essence of problem decomposition in computational thinking. To close, here is a short activity for you. Think of another everyday or academic problem: planning a trip, organizing an event, or solving a physics question. Try to decompose it into 4 to 6 subtasks, just like we did for the coffee machine and the GCD.